So our next section is on flowchart thinking. We're learning kind of how to make proofs. These last section 4.6 is about writing proofs and using CP, CTC. Now in this chapter you might be saying, you know, we're just doing too much writing in here, Mr. Meyer. I mean, we shouldn't have to write in math class, right? Well, you know, mathematicians do hate writing, so we've come up with some things to help limit writing. So what we want to talk about today is how can flowcharts express a proof. So you're making a deductive argument about why something is true. A flowchart cuts down on the amount of writing you do, and it also shows connections a little bit more easily than you can with words. So this is oftentimes becomes students' favorite way of giving a deductive argument. So I want to teach this to you today so you can learn not only can you write a paragraph proof, but you can also write a flowchart proof. I think you'll like this. It saves a little bit of writing and makes things a little clearer. So as we get started in on talking about how to do flowcharts, we're going to use the same reasoning we've been using up until this point. But I want to be explicit about the two steps there are for creating a proof. So in your notes there you have some blanks to fill in here. You know, there are two steps in creating a proof. A lot of times students mix these together and they don't realize that there's two steps. And so they're kind of trying to skip step one and go right to step two. Step two is where you actually write the proof. But step one is understand why something is true. And you try different ideas, you mess around with things, you mark all the things you see as congruent. You try different ways of figuring out what's going on until finally you realize, oh, if I use, if I have parallel lines, then I have congruent alternate interior angles. And if I have those, and oh, here I have vertical angles. So you notice all these things in your picture, and using conjectures or definitions or properties that we've already learned, you begin to amass this set of things which is true, and suddenly you can use a triangle congruency shortcut or something like that in order to write your proof. So the first step, before you can really write anything, is do you understand it? Have you explored your picture? Have you found everything that could be congruent? And that's how you start. Maybe you don't even use everything you found, but you're kind of exploring it until you put the pieces together and realize, oh, if I have these three congruent pieces, then I can use the triangle conjecture, then I can use CP/CTC to say that this particular part is. So that's what step two is. After you've played with it, you've found out everything that you can about the picture, you've used all the properties and conjectures that we have, then you're going to put that idea into a paragraph or a flowchart where every statement's followed by a reason, and it explains how to get from the previous statement to the new one, previous statement to the new one. It's a step-by-step. I call this playing proof. We want to play proof after we understand it. We have to slow down, go step by step through something and put it into a proof format where every step has a reason that is a conjecture or a definition or a property that we've learned. So let's talk. What I want to do is look at a proof that we're trying to do and then show you what this looks like in flowchart form, and just so we can kind of explain things. Then we'll highlight the rules for making a flowchart proof, then we'll actually create one on our own. So let's go through that now. So right here, first we want to understand this. And to figure it right, EC is congruent to AC. So I'm going to start marking up here. I'm going to try to understand what's going on. And one of the ways I do this is by marking up my picture as I move along. So as I read things over here red, I'm going to mark them. Segment EC is congruent to segment AC, so that means these two things are congruent to each other. ER and AR, these two are congruent to each other. And the question is angle A congruent to angle E? If so, give a logical argument to explain why. Well, A and E kind of look the same, that's for sure, but that doesn't help me here. And my idea is if I can prove that the triangles are congruent, that's what I think I'm going to do. If I can prove that this triangle on the top is congruent, say, to this triangle on the bottom, then since the triangles are congruent, I'll know that all the corresponding angles are congruent, and that means the angle between the angle E and angle A would be congruent to each other. So now I'm trying to think, why are these triangles congruent? I see that I already have two sides that are congruent here, and so I just need to have one more side that's congruent. And can you see another side that's congruent or an angle that's congruent? Anything else here? Well, I hope you see that both these triangles have RC in them. This is the third side of both of those triangles, and obviously, since they share this side, that's congruent to itself. And so I have two triangles which are congruent. I have three sides that are congruent to each other, so by side, 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 I know that they're congruent. And once I know that they're congruent, I can use CPCTC to say, oh yeah, by the way, this angle right here, angle A, and this angle right here, these are corresponding angles. Those have to be congruent. So first, this is what I'm trying to understand here. So I've kind of gone through step by step, and I've figured out why this is true. Well, now I want to take a shot at the proof. Now this is what the proof looks like. The proof looks like something like this. And I just want to explain to you kind of what we have here. So you can see that here in this proof, I put boxes around the statement. So here we have segment AR congruent to segment ER. And the reason that is given, that's a given because it's right up here. They told me that when I started off my proof. Same with segment EC is congruent to AC. That's given too. And then I added the third piece of the puzzle that needed to be done before I can get the triangles congruent. Now, I realized that also we had to have this third side, which is congruent to itself here too. Let's make that in red. Okay, so this third side is congruent to itself. RC is congruent to RC. And the reason for that is the reflexive property. If you remember, that's something is always congruent to itself, or something is equal to itself. Reflexive, like reflective, like a mirror. That's the reflexive property. Now, because these three things are true, you can see I have a side here, I have a side here, I have a side here. I have three sides that are congruent. Because of this, I put these three arrows and I tell you that the triangles are congruent to each other. And that's by the side, side, side congruence conjecture. Now, you don't even really have to put congruence conjecture after side, side, side. I just put SSS there. Now finally, my last step was to notice that A and E are corresponding. And so here in my very last box, I tell you that angle E is congruent to angle A. You always want to have your statement that this is what I was trying to prove right here. I was trying to prove that angle E equals A. That thing is always going to be what you put in your very last box here. So angle E is congruent to angle A is what I end up with. The reason I can make the step from the triangles being congruent to those angles is because corresponding parts of congruent triangles are congruent. When you have a congruent triangle, you have 6 pairs of things that are congruent. In particular, one of them is that angle E on the top is got to be congruent to angle A here. I can see that because right over here in my congruence statement, I have E and A in the third spot, so I know that those two things are congruent to each other. So that is a great example of a flowchart proof. So let's see, what if we had a shot at this? So let's try here. Let me highlight some flowchart rules for you. The first thing I want you to know is that you put your statement inside the box. It doesn't go outside the box. You always put a statement and then you make a box. So write your statement first. Don't make the boxes first. It doesn't work as well. Write out your statement. Put a little box around it when you have a flowchart. The second thing is that you put your reason for your statement under the box. So you saw before we would list something and we'd say given, or we'd list something and say SSS congruency conjecture. So the reason for the statement goes underneath the box. That's the why that step can be taken. And finally, arrows show logical connections. In other words, if this is true, then this has to be true. So for example, I had to have side-side-side congruency, I better have 3 sides that are congruent. So I had all 3 of those boxes with an arrow going to the same conclusion, which was that the triangle was congruent. It needed to have 3 sides congruent in order to have that, and that's what we saw there, were those 3 sides. So these are the flowchart rules: statement in a box, reason under the box, arrows showing what things are connected to each other, what things are relying on each other. So let's work out a problem here. Let's create our own flowchart proof. This is actually a proof that the construction for an angle bisector actually works. We couldn't really prove this before, but now that I know about congruent triangles, I can prove to you that if you take your compass and you mark an equal mark, that's what this arc AC is. It's an equal mark on one side of the angle and an equal mark on the other. Then you move your compass and put your point on A, and you draw. You can set your compass anywhere again. It doesn't have to be the same. You make a mark there, and then you put your compass point on C and make a mark where they cross D. It will be the same distance from both of those. And we're going to prove that this BD, the line, the ray that starts at B and goes through D, is in reality the angle bisector of that. So the first step here is to figure out why this is true. So I'm going to play around a little bit here. Before I get to my formal proof, I want to do step 1, which is understand why it's true. So I notice that I have a triangle. I'm immediately looking for triangles. And I notice that I have a triangle that's right here. And I got a second triangle that's down here. Oops. So I have these 2 triangles. In order for me to say that BD is the angle bisector, I need to say that angle 1 and angle 2 are congruent to each other. So if I could prove that angle 1 is congruent to angle 2, that's the definition of a bisector. An angle bisector splits up an angle into 2 equal angles. And that means that angle 1 and angle 2 would be congruent to each other. But angle 1 and angle 2 are both in these triangles. And in these triangles, I can see I already have sides that are congruent here. I have 2 sides that are congruent. So I'm going to move these just so I can see a little bit better. But what I see is that this side and this side are congruent to each other, and then this side and this side are congruent to each other. I just need one more side to be congruent to each other. And I hope by now you're kind of getting this feel here. Where would my third side come from? Well, BD is congruent to itself. It's a shared side. And that means that it is going to be congruent to itself. And that is the third side of my triangle. And that means that these 2 triangles are congruent by side, side, side. I have 3 sides which are congruent. So I just need to say the givens. That gives me 2 sides congruent. Then I'll need to say that BD is congruent to itself by the reflexive property. Because of those 3 things, I have the triangles being congruent. Then, because the triangles are congruent, angle 1 and angle 2 are congruent to each other. And that means that BD is bisecting the angle because it split it into 2 equal pieces. So this is my first step in every proof, which is to figure out why it's true. And then my second step is to play proof, to make something pretty here with my proof in order to be finished here. So step 1, idea. Step 2, play proof. I'm going to need to have statements with reasons that are followed by each other. So my first step here is I'm going to say, remember I want to use side, 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 so I'm going to list each of the sides that are congruent to each other. So I'm going to say BA, that side is congruent to a BC. Now the reason I know that is because they gave that to me right at the very beginning. Let's see, having a little trouble here. What I was trying to do was after... yes. There we go. In a flowchart proof, after you draw a statement, then you draw a box around it. That's what I was trying to do. And this is given. I also had that CD was congruent to AD. And why was that true? That was also given to me. And you know what I mean by given here? What I'm saying is that right here, okay, that's what's given to me. Those are the things that I can use when I'm doing my proof. Now that was two sides. Now I also noticed that right here, this third side was congruent to itself. So I'm going to write that down now. And that wasn't given. Why was that true? Remember what that property is called? The one that says that everything is equal to itself? That's reflexive. So the reflexive property tells me that. Now because these three sides are congruent, I can say now that the triangles are congruent. That's exciting. So I get triangle, BAD, BAD. It's congruent to triangle. Let's see, what corresponds here? B is congruent to B, and A is congruent to C, and D is congruent to D. Flowchart proof here. Put these right next to, I put a box around these here. I'm going to try to make my box a little smaller because I'm running out of room here to do my flowchart. I'm trying to be careful. The reason for this one is side, side, side. The side, side, side congruence shortcut. Now I need to put in some arrows to explain where things are coming from. So I'm going to put in some arrows to say I need three sides in order to say side, side, side. There's one side, there's two sides, and here's three sides. These are the three things, the three sides that I need in order to tell you that this is true. Now that I have these two triangles congruent to each other, I can say that the angles are congruent to each other, that angle 1 is congruent to angle 2. So I get angle 1 is congruent to angle 2. Why was that true? Well, that's because once the whole triangle is congruent, it means that any of the corresponding angles are congruent, and that's called CP, CTC. Corresponding parts of congruent triangles are congruent. I need to have an arrow that goes in here as well. I'm just going to have a little tiny one that goes from this one to this one. So now I have that my angles are congruent to each other. But if angle 1 is congruent to angle 2, that means that that angle's being bisected. So the very last thing that I'm going to say then is I'm going to say that BD bisects angle ABC. Put a box around that. Flowchart proof, I have to write underneath why that's true. This is what the definition of a bisector is. A bisector is something that splits something into two even pieces. And that's exactly what has happened here. And I just put one last arrow here that comes down there. Now notice that I always end with, in the middle of my flowchart here, the thing in the very bottom box, the last box in my chart, has to be what I'm trying to show. I'm trying to show that BD is the angle bisector of that angle, and sure enough, that's what I ended up with down there in my very last one. So that's an example of a flowchart proof. It's another way of expressing an argument. You can see it's not as many words. Those of you who are less wordy might like this method. You just have to give a statement, put the reason underneath, and then use arrows to show the connections. It's a way of expressing a logical argument in a little more visual kind of way.